Welcome to week 2. One important topic in satellite communications is the satellite orbit itself. Now, before we understand the orbits, we have to look into few of the coordinate systems that are used to describe such orbits. After that, we will look into the typical Keplerian orbits and the elements that can describe a certain orbit, its inclination, its rotation, its radius, and so on. After that, we will look into propagators, or if you want, simulators that can simulate a satellite orbit if you give it the time and you give it the required propagation. When do you want to expect the satellite to pass? After that, we will look into the satellite axis or the tracking of the satellite. That is, if you have a ground terminal, what is the location of the satellite with respect to the ground terminal? So that means if I'm a ground terminal, what is the azimuth and elevation of a satellite, and what is the range between myself, I was a ground terminal, and the satellite? These are very important parameters for later on for communication link calculations. I hope you'll enjoy this lecture with me. We will first start with the most common coordinate system, which some people call it the GPS coordinate system. Like someone asking you, what is your GPS coordinates? Well, the actual name, or the correct name, should be Geographic coordinate systems. And the answer would be latitude, longitude, and your altitude. So let's have a look at here, closer look at what are these three parameters. So suppose you are at this point. Your latitude will describe your angular spacing between the equator of Earth and your point. Your longitude will describe the spherical angle between a certain reference line, which is called a datum, or the prime meridian, towards your location. Now, that datum or prime meridian is near to Greenwich in UK, and as you can see here, there is a photo of someone standing at exactly a longitude of 0. Now, for these are well described in the WGS 84 system, which define the standard datum used in the geographic coordinate systems. Now, for a satellite can still be described as well in a longitude, latitude, and altitude. Of course, it will not be on the Earth's surface, it will be far above Earth. In our day-to-day experience, it's much easier to describe points in terms of their distance in meters or kilometers. And here comes the second coordinate system, which we're going to talk about, is the local Cartesian coordinate system. So suppose you have a bunch of points. Here, this is near to Melbourne, and these points are described in terms of latitude and longitude. And someone asks, okay, so what is the distance between 2 points here? It's really hard to intuitively understand that. However, if I use, these are the same points, if I convert them into a Cartesian coordinate system, it's much easier to see the distance between 2 points here, or the average distance between the points. However, in order to do this conversion, you need a reference point. So I provided here a reference point, and then all these circles are referenced towards this point. And you see here the reference point has a coordinates of 0, 0. Now it's worth mentioning that the y-axis in this particular conversion is aligned with the north direction, and the x-axis is aligned with the east direction. Now you can use Matlab to do this conversion. So these are called conversion between LLA, or latitude, longitude, altitude, to local Cartesian coordinates. And you typically need to use a reference system such as the WGS 84 system, and also need to specify a reference point where do you want this Cartesian coordinates to be referenced to. The previous two coordinate systems can be used for satellite or can be used for typical day-to-day activities. However, for satellite applications, there are two coordinate systems that are much easier to use to describe a satellite orbit or a satellite location. The first coordinate system is called the Earth-centered inertial. So in this coordinate system, the satellites are independent of the Earth rotation. So, because a satellite, they don't care if the Earth is rotating or not. For them, the satellites, all what they care is about the mass of Earth. So in that sense, the ECI, or Earth-centered inertial, is fixed with respect to the stars. To the contrary, the Earth-centered, Earth-fixed ECEF coordinate system is rotating along with the Earth. So that you can see here the blue coordinates are rotating with respect to the ECI frame. We will see much more details in the upcoming 2 slides. The figure on the right side shows both the ECI and the ECEF coordinate systems. So now, as an observer, we are fixed with respect to the ECI frame. So here's the ECI, and the ECI frame is fixed with respect to far stars. Okay, now let's see where these axes of the ECIs are pointing. Let's start with the z-axis, is the easiest axis. So the z-axis is fixed with respect, is aligned with the Earth rotational axis. So that's the axis where the Earth is rotating about. Okay, now the x and y plane, so xy plane, is then aligned with the equatorial plane of Earth. Okay, now how do we point the x and y direction? Where do we point x? Why is it point to this particular location? There are different reference points where we can orient your x vector. One of the references, for example, is called the J2000, where the x-axis is pointing to the vernal equinox at a particular time. On the other hand, the Earth-centered, Earth-fixed coordinate is fixed on the Earth. So it is rotating along with the Earth rotation. So here the fixed refer to it's fixed with the Earth. And what you can see here, the z-axis is also aligned with the rotational axis of Earth. The x-axis passes from the point, this point here, which is having a latitude of 0 and longitude of 0. And the xy plane is also in the equatorial plane, aligned with the equatorial plane of Earth. Now, the ECEF coordinates completes one rotation every 86,164 seconds, which is, if you do the math, this is approximately equal to 24 hours multiplied by 60 minutes multiplied by 60 seconds. Now you'll find there's a difference here because our actual experience of a day has to do with the illumination of the sun. But the rotation of Earth itself is slightly different. It's called one sidereal day. It's slightly different than our actual experience of a solar day. Now we will see in the lab how to do the conversions between the ECEF and the ECI. It's worth noting here, if you have a point or a satellite that is described in the ECI frame and you want to convert the coordinates from ECI to ECEF, you need to know the time where do you want to do the conversion, because at different time points you will get different results. The last coordinate system that I would like to cover is called the azimuth elevation range system. This is a very important coordinate system, perhaps the most intuitive way to describe the position of a satellite with respect to a ground station. So we are standing at this point on the Earth's surface. Here is the north direction, here's the east, south, and west. Now, the elevation of the satellite, if you look at the sky, the angle between the horizon, so this circle represents the horizon, between the horizon and the satellite is called the elevation angle. Now, the rotation of the satellite with respect to the north, so the north is the reference point. When you rotate clockwise with respect to the north, this is called the azimuth, and then the range is the distance between you as an observer and the satellite. These coordinates are quite important for satellite communication. And as we will see also in the lab, we can convert between all the previous coordinate systems using built-in functions, or also you can build your own functions to do this conversion. One way to show the positions of satellite with respect to a ground user is a sky plot. What is a sky plot? In the sky plot, you are sitting at the center of this plot. And let's say if we have a satellite at this particular point, it shows here that our azimuth is 30 degrees. You see here, this point 30 degrees. And our elevation is 20 degrees. So the distance or the angular distance between the horizon, so this circle represents the horizon. And as you go away from the horizon, so we have 0, we have 20 degrees, 40 degrees, we have 60 degrees, and then finally here we have 90 degrees. So this point represents the zenith, means if you have a satellite at this point, it means it is right above your head. Let's take another example. This point is or this satellite is at an azimuth of 120 degree and an elevation of 40 degrees. You can do this exercise, you can go ahead and do this exercise using skyplot command in Matlab. There are also software or apps you can download in Android. For example, this is a nice app called GNSS Status. It will show you the current position of different GNSS satellites. GNSS mean such satellites as GPS, GLONASS, or Galileo, or Baidu. It will show you their positions with respect to you, your phone, in a particular moment. For example, let's take this satellite. It looks like it's a GPS satellite, GPS BRN5. At this particular moment, it was at an azimuth of 30 degrees and an elevation. So I assume this would be the horizon. This would be 30 degree elevation, 60 degree elevation, and 90 degree. So that satellite, for coincidence, is around azimuth of 30 and elevation of 30. On the other hand, let's look at this satellite. This is at azimuth of 120 degrees and elevation of 60 degrees. It's not a surprise that Earth is not a perfect sphere, but rather is slightly oblated because of the rotation of Earth. So what you will find that the radius between the center, for example, the distance between the center and the north or south pole, is a bit shorter than the center and the equatorial plane. For this reason, when we convert between LLA, longitude, latitude, altitude, to local Cartesian or to ECEF or other coordinate system, we need to take into account the oblateness of the Earth, and that is the Earth is not an ideal sphere. We will use the WGS 84 as the reference ellipsoid. So this shape is called an ellipsoid. It's a slightly pressed sphere from the north and south poles. We touched on the types of orbits in the previous lecture. Let's do a quick refresh and dive in more depth on these types of orbits. So we have first the geostationary orbit, which rotates with the Earth rotation, so it completes one rotation approximately every 24 hours. So it appears almost stationary for an observer on Earth. We have the medium Earth orbit, and we gave example of GPS and Galileo constellation. And finally, we have the low Earth orbit, which are used typically for communication satellites and also for Earth observation. Keplerian orbit is a simple method to describe the rotation of a celestial body, in our case, the satellite. They are referenced to Johannes Kepler and can be derived based on Newton's classical law of gravitational force, which you have it from high school. The force acting between two masses m1 and m2 is proportional to the masses and inversely proportional to the square of the distance between the two masses. A Keplerian orbit takes the form of an ellipse. In this ellipse, we have Earth at one of the centers of the ellipse. Note that the ellipse has two centers, and the satellite rotating around Earth in an elliptical orbit. The point where the satellite is the closest to Earth, we call it the perigee. The point at which the satellite is furthest to Earth, we call it the apogee. Note also that an ellipse has two semi-axes. So one axis called the semi-major axis, which is denoted as A, is the distance between the center and the apogee, or the center with the furthest point in the ellipse. And the distance between the center and the closest point of the ellipse, we call it the semi-minor axis, and it's usually denoted as B. Now what happens here, if A equal to B, we will end up with a circle, and the two focus points of the ellipse collapses to the center. So there is a parameter called the eccentricity, which describes how elliptical an ellipse is. What does that mean? If you substitute A equal to B in this relation, what you will get is eccentricity of 0. Eccentricity of 0 refers to a circular orbit. You will get a perfect circle. Last concept in this slide is the true anomaly. The true anomaly is the distance, the angular distance between the satellite position and the perigee line. One of the interesting observations of Kepler is that celestial bodies travel or sweeps equal areas in equal interval. What does that mean in our context for satellites? Let's assume you have a satellite at this point, and let's call it A1. And let's assume after 5 minutes, we check the location of the satellite, we found it at this position B2. So the area swept by the satellite, let's denote this area as A. And let's wait some time, and then again check the position of the satellite. And let's say the satellite is at a position A2 as I'm pointing to. And after 5 minutes, we check the position of the satellite. We found it at a position called, let's call it B2. Now the area swept by the satellite between A1 and A2 and B2, you will find that this area is exactly equal to the first area. A third example, if a satellite at a third time interval is at position A3 and after 5 minutes is at a position B3, what you will find that the area swept in this 5 minutes is equal to the second and the first areas. So this can also be deduced using Newton gravitational laws. This is called the Kepler second law. Another concept I would like to introduce that we will use later is called the equivalent principal circle. The principal circle is a circular orbit, so if I replaced this elliptical orbit with a circular orbit with the same period, this is called the principal circle. A third important observation of Kepler is about the period of the orbit. How much time does a celestial body require to complete a full rotation around the other celestial body? So in our case, we have Earth and we have the satellite. So the question here, or the law, is about the time required for the satellite to return back to the point that it started with. So what the law say that the period is 2 pi square root of the semi-major axis. So A is the semi-major axis of the ellipse. So here's the semi-major axis. This is A. And you use the parameter called mu. Mu is a gravitational or standard gravitational parameter, and is related to the planet that the satellite is rotating around. For example, for Earth is known to be 3.9, etc. And for Mars there is another parameter. So for each planet you will find there is different mu. And that depends, of course, on the mass of that planet. This is a nice application of the Kepler's third law. It's asking us to calculate the altitude of a geostationary orbit, and it's providing us with the length of a sidereal day in hours, minutes, and seconds, and also providing us with the equatorial radius. Let's make a simple sketch showing the different parameters. So remember, a geostationary orbit, if you place a satellite in a geostationary orbit, it will rotate, first of all, it's a circular orbit, and it will rotate at the same rate as the Earth rotation. So here's another point, which is called the satellite subpoint. So what I'm taking here, this is a slice of Earth at the equator, so this is the equatorial circle. Now, it's asking us to calculate h, which is the altitude of the geo satellite. I'm going to put here geo. That's this x is the center of Earth. That's the satellite subpoint, so I'll call it just SS. And it's giving you also the radius, or the average radius of Earth at this equatorial plane, which is about 6,378. Now it's also giving you the sidereal day, which is the amount of time required for Earth to rotate around itself. And you will find, okay, why this is not 24 hours? Because we explained previously that our experience of the solar day is different than the rotation of Earth, because solar day depends also on the rotation of Earth around the Sun. Now, let's see what can we do for that. First of all, we obtain the period. So if you take 23 hours multiplied by 60 minutes multiplied by 60 seconds plus 56 minutes multiplied by 60 seconds plus 4 seconds. So if you do this calculation, you will end up with something similar. This is provided with fraction, just a bit more accurate. All right, now we have the period. This is the amount of time that the satellite should be rotating around Earth. Can we use the Kepler third law to calculate now the radius of that orbit? Well, if you remember, the law says if you have an orbit with a semi-major axis of A, what you do, you cube that, you divide it by the gravitational constant of the planet, you take the square root, you multiply by 2 pi, and you end up with the period t. But now we have t, we want to obtain A. Easy, no problem. So you just rearrange this equation and you end up with this equation. This one shows the relation between the semi-major axis. Now remember, this is a circular orbit, so basically this is the radius of the orbit based on the period of the orbit. So this, if you do the calculation, you will end up with this amount. Now, this is the radius, this is not the altitude. The question is about the altitude. I'm gonna draw the same drawing here, but from top view. So what you will see here, this is not to scale, all right? So here's the orbit, here's the satellite, and here's the satellite subpoint. Now we calculated the total distance. What we want is the height, and we have the Earth radius, so we calculated the overall distance, which we called it the semi-major axis. So all what you need to do now is to subtract RE from the A, and that's what the third step is doing, is taking the total radius, subtracting RE, so then you can obtain the altitude of the satellite. This is a very important number, and you will see that we are going to use it in the upcoming lectures, also in the labs. An elliptical Keplerian orbit can be described using 6 parameters, and naturally we call these parameters our Keplerian elements. Now we're already familiar with some of these elements. We saw how the semi-major axis described the ellipse. We saw also how the eccentricity described the ellipticality of an ellipse, and we saw that if we have an eccentricity of 0, the ellipse collapses into a circle, while if you have an eccentricity of 1, the ellipse becomes a parabola. It's not really useful for satellite communication, but just to let you know that the eccentricity has a value between 0 and 1. Now the third parameter is called the inclination, which describes how the orbit is rotated or inclined with respect to the equatorial plane. So in this figure, we're showing the satellite orbit. This is the orbit of the satellite in blue, and this plane is the orbital plane. And then also we're showing in green the equatorial plane, and remember the equatorial plane is the plane passing through the equator, and also is aligned with the XY axis of the ECI frame and the ECEF frames. Now the angle between these two planes is called the inclination. The fourth parameter is called the right ascension of the ascending node. Alright, it's a mouthful of term, but let's see what is the ascending node. What's a node? So the node is the point where the two planes intersects, the plane of the satellite orbit and the equatorial plane. We have two nodes. One is called the ascending node, and note here this is the direction of the satellite. So the point where the satellite goes from the south hemisphere to the north hemisphere we call the ascending, and the node, the point where it's going from the north hemisphere to the southern hemisphere, we call it the descending node. Now we don't really care about this. So the angle that is formed between the ascending node and the reference x-axis of the ECI frame is called the right ascension of the ascending node. Why is it right? Because going to the right direction. This is and it's usually denoted as omega. So note that this is rotation along the z-axis, of course. The fifth parameter is the position of the periapsis. Now, what is the periapsis? Well, periapsis is just the perigee. Remember, the perigee is the closest point between the satellite and the Earth center. Now, this is not 90 degree. Maybe in this drawing it shows it as it is very close to 90 degree. This could be anywhere. So if you rotate the orbit in the direction of my movement of the pointer, this is called the periapsis. Now, these 5 parameters are sufficient to describe the orbit itself. But then we need to have a 6th parameter which describes the position of the satellite within the orbit. And this is the initial true anomaly, which, if you remember, I'll show you the true anomaly is the angular distance between the periapsis of the perigee and the satellite. Now we have 6 elements. These 6 elements can describe the position of the satellite perfectly within an orbit. This is an interactive example of a Keplerian orbit. So we can see here the Earth, we can see the x-axis, the y-axis, and the satellite position here is in a small red point. This is the z-axis of Earth, this is the rotational axis of Earth. Now, the orbit is said to be as exactly as the radius of Earth. So first parameters is the semi-major axis. I'm going to increase that. So you see here the semi-major axis is increasing. And now because we have a perfectly circular orbit, so the semi-major axis is equal to the radius of the orbit. Okay, let's have non-circular orbit. We can have that by increasing the eccentricity. So when I increase the eccentricity, note what's happening. The orbit is becoming more like an ellipse. Now, remember in an ellipse, the Earth's center here occupies one of the focus points, and in this case, this focus points of the ellipse. Now,
let's continue with the parameters. So here we can see the satellite more clear. If I increase the inclination, look what happened. So that's the inclination of the orbit is changing. Now, how about the argument of periapsis? So the argument periapsis, if you look at the previous slides, changes the rotation of the orbit within the orbit itself. So look at that. So I'm changing now the small omega. So it's changing here. The orbit is rotating, but the rotational axis is perpendicular to this orange plane, which is the plane of the orbit. Now, if I increase the big omega, which is the right ascension of the ascending node, the orbit will rotate around the blue, or the z-axis, which is perpendicular to the to the equatorial plane, which is the blue plane. Look what will happen now. I'm increasing that. So you see the orbit is rotating around the z-axis. For small omega, the orbit is rotating around the axis of the orbit itself. Now let's have a look at the, let's set this to some nice value, for example 90 degrees. And let's have a look at the satellite when we change the true anomaly. So this is the initial true anomaly. So here I'm increasing the anomaly. The position of the satellite is changing. The orbit is not changing, but the initial position is changing. So here we have the true anomaly is 0. And if I rotate it, this is 180 degree. Let's put it 180 degree. So it should be on the opposite side. And if I rotate it all the way back, it will come back to the perigee point.
You can also create an orbit using Matlab as an example. So what I'm providing here for you, a custom-made function called GenOrbit, which I wrote previously, that accepts different elements. So these are the 6 elements. Let's have a look at this code in details. So basically, I'm just defining the Earth radius and the height or the altitude of the orbit. And if you add the average Earth radius plus the height, you end up with the semi-major axis. So that's our first parameter. I'm also entering the eccentricity. I'm having an inclination, the omega. This is the small omega, which is the argument of periapsis. And we have the big omega, which is the right ascension of the ascending node. And also we have the initial true anomaly. So in total, we have 6 parameters describing the orbit of the satellite. And then also I'm putting the mu of Earth, which is the standard gravitation parameter of Earth, number of periods that I would like to simulate. For example, here I want 1 period, and the propagation time step. So I need to simulate every 10 seconds of that orbit. And also I want to simulate the orbit, 1 full orbital period. So that's why I'm calculating the orbital period based on the provided A and mu. So also we have a parameter called t, which is the time series. Now, if you feed the parameters and elements to that function, it will produce for you an orbit, and you can plot this orbit. So it's a homework for you to try this example that I have attached with this course. So you can download this from Canvas. In this slide, I'm showing a comparison between the online tool that we saw in a couple of previous slides versus the Matlab code that I provided you. And you can see when you input these parameters, you get the same results. Now, in real-life satellite applications, we use what is called the two-line elements. Now, why they are called two-line elements? Because they are 2 lines. And this is kind of a de facto standard of describing satellite orbits. You can go, for example, to this website, and you can download freely, for free, all the current satellites that are orbiting Earth. But they all will be in the 2-line element format. Now, if you look at the 2-line element format, it includes the 6 Keplerian elements, but also includes other parameters that will help you to calculate the orbit in more accuracy using different methods than the Keplerian method. So what we've learned so far is how to find an orbit based on Kepler motion. However, we will see that because Earth is not perfect sphere, it has also a regular gravitational field. So some areas are having more gravity than other areas. We're also having some atmospheric drag. That is because the atmosphere does not stop at a particular altitude. It's gradually decay into space. So satellites are pressured a little bit with the atmosphere, especially low Earth orbit satellites. Also, there's a radiation pressure from the sun, and also there's a gravitational field from the sun and the moon. So when these taken into account, you need more advanced, and it's very hard to do manual calculations for that, so we use codes to simulate the satellite orbits. So in order to simulate the satellite orbit, you need to feed it with the two-line element. This is an example of the International Space Station and code word Zarya. You can download the updated two-line elements from this website. This is an example on how to use the two-line elements and feed them to Matlab, such as it can produce for you an orbit. Now this is a built-in function in Matlab. So what do you need to feed it with? The start time, and for example, this is a start time that I selected for the simulation. The stop time, when the simulation you want to end, and I will simulate here for 2 hours. The sample time, how much the interval between the sampling point. So the less number, they will take more time to simulate because you have more samples. The higher the number, the accuracy will be lower, but it's okay for our illustration purpose. Then you need to create the scenario. Now, this example is just a rough example. During the lab, you will go into much details how you will generate your own orbits, and you will study it in much more detail. We are generating the satellite scenario, and then we are generating the satellite, and after that we are displaying that satellite. So if you run this video, you will find this is the International Space Station based on the downloaded elements from the website that I've mentioned before. An orbital propagator is a simulation tool that you need to feed it with the elements of the orbit that describes the orbit. For example, in the previous example we fed with the Keplerian elements, we also fed it with the time of simulation, and then it produced for us an orbit, a satellite orbit. Now similarly, we saw another example where we fed a tool with the TLE, two-line elements, and also we provided the start and the end time of the simulation, and also we found the orbit, and that was a simulation for the ISS station. Now in the upcoming couple of slides, we will dive in deeper on how these two different orbital propagator, now these are simple, this is a very simple propagator, the Keplerian propagator. We will also look at another propagator called the SGP4, but there are also many other propagation methods that are out of the scope of this course. The first propagator that we will look at is the two-body propagator, which is the simplest propagator, and also called the Keplerian propagator. It assumes that Earth has a uniform gravitational field. It means the Earth mass is uniformly distributed, and actually you can collapse the whole mass at the center of Earth. And what does that mean? This is based on Kepler's observation that the orbit will be in a perfect ellipse shape. There are two steps to generate the orbit. First, you need to generate an ellipse, because we know that the orbit is an ellipse. But second, you need to rotate that ellipse. There are 3 rotations that you need to apply for the ellipse. So the first rotation, you need to rotate. So here's the base, here's the ellipse. Now the first rotation is that ellipse need to be rotated. So from this state, it will become as, here's the Earth again, it will be rotated. And this rotation, we called it the argument of periapsis rotation. The second rotation, we need to rotate the orbital plane itself against the equatorial plane. So I'm going to draw an equatorial plane, and here is the orbital plane. And this angle between them, we called it the inclination. Now the third orbit, so this is the first, the second is the inclination. The third rotation that we need to do is we need to rotate the orbit itself around the z-axis, and we call this rotation as the right ascension of the ascending node. Now you don't have to do this, don't worry about them. This is for your info, the upcoming slide. This is for your info of how to generate an orbit yourself, how to design a propagator yourself. However, in all the examples that will be provided, you will use a built-in propagator in Matlab. This is for you to understand in more depth how the orbits work. Let's have a deeper look into how to generate a Keplerian orbit. The first step, as we said, is to generate the base orbit, which is an ellipse. In order to draw an ellipse, you need to know the semi-major axis, which is an input parameter, and also the eccentricity E. A satellite at the beginning, as we said, it's at an angle nu, which is the true anomaly, and at a certain distance, let's call it r. So what we need to do now is to find the series of points on this ellipse that the satellite will be positioned at every time instance. So for example, if you have a time vector, let's call it from 0 and 1 second, 2 seconds, 3 seconds, etc. and up to the last point would be t. So at point t, the satellite will return back, t is the orbital period, the satellite will return back to the starting point. So what we need to know the radius, r, at each of these time intervals, and we need to know the new angle, or the true anomaly, at each of these time intervals. So if we can build these two vectors, so vector means a series of data, if we can build these two vectors, then we can draw the orbits. There are a couple of steps needed before we can generate our vector, r vector, and new vector. Remember, these vectors are needed such that we can generate an ellipse. First, let's remember the concept of the principal circle. We introduced that a couple of slides ago. So what is a principal circle? It's a virtual orbit that if you place a satellite at the virtual orbit, and here's your real satellite, I put it in blue, both the blue satellite will have a orbit t and the virtual satellite will have orbit period t. But the nice thing about this virtual orbit that it has a uniform circular motion. So what does that mean? If you want to know the mean anomaly, we call this the mean anomaly with the position of the virtual satellite. If you want to know this mean anomaly, all what you need to know is the time t. So in one period, capital T, the satellite will make 1/4 circle, so we'll make a 2 pi. So in a small time t, the satellite will simply make t over capital T multiplied by 2 pi. So what does that mean? It means the mean anomaly of the virtual satellite is simply 2 pi small t divided by capital T plus the initial mean anomaly. And then according to Kepler, so I'll show you here the difference between the true anomaly and the mean anomaly. So remember, Kepler said if for equal period you will pass equal areas. So at this point, I'm going to draw this in blue. This is your actual satellite. After, let's say, 2 time clicks, it's at this position. Now the red satellite, after 2 time clicks, it is at this position. So if you run the simulation, the virtual satellite will pass this amount in angles, and the actual satellite will pass this amount. So I'm just going to draw it on top of it in terms of angles. So the true anomaly at this point is equivalent to the mean anomaly at this point at a certain time, simulation time equal to t. There are 3 equations here in this slide that I'm not going to provide the proof for them. You can refer to any of the orbital mechanic books and if you are interested in the detailed proof. But what these 3 equations tell you, that if you have the expression for the mean anomaly, or if you have the vector of the mean anomaly, and yes we do, because remember, we have the t vector, which is the simulation time. For example, we are simulating 0, 5 seconds, 10 seconds, etc. up to a period t. You can calculate the m vector from it, and we saw the simple equation how to calculate it was just 2 pi t over capital T plus the initial mean anomaly. So we know m. So this equation will tell you you can calculate what is called the eccentric anomaly, which is denoted here as E, and based on the eccentric anomaly you can calculate the true anomaly and the radius of the orbit. Remember, these are what we needed for generating an ellipse. Now these are polar coordinates, so let me just review what we said. If we have a simulation time vector t, for example 0, 5, 10 seconds, etc. up to a period t, you can then deduce the vector r, which is the distance between the Earth center and the satellite, and also you can deduce the vector nu, which is the angle between the x-axis and the satellite. So if I'm making here a simple drawing, I want to convert these polar coordinates into Cartesian coordinates. So all what you need to do, here's the r, here is angle nu, here's the satellite, let's call it here sat, and this point at the center is Earth. So and here's the x-axis, here's the y-axis. So basically x is simply r multiplied by cosine u, and the y value is r multiplied by sine u. Now, the orbital plane, this is the base plane we're generating, is still in the xy plane. So the orbital plane is still in the xy plane. So that's why all the z's are 0. We will see in the upcoming slides how we will rotate this base orbit in 3 dimensions.
We will see here an example of how the 3 rotations are applied as part of step 2. So first, look at the white orbit. This is the base orbit, and you can see the base orbit now is aligned with the xy plane. The first rotation is around the z-axis. Here's the z-axis, and we're going to rotate with an amount small omega, which is the argument of the periapsis. So note here the rotation is happening around the z-axis. Here's the z-axis, and we rotated with an amount small omega. The second rotation is around the x-axis and will be with an amount of the inclination, and see what will happen. So this is the x-axis, the green line, and now I'm rotating and see what's happening. I'm rotating around the green line. The third and the last rotation is around the z again. So here's the z-axis, and I'm going to rotate with an amount big omega, which is the right ascension of the ascending node, and see what will happen. It's rotating around the z-axis. Now, of course, in the simulator here, it doesn't matter which order of rotation you apply. However, when you're writing the script, the rotation should be in order, so you end up with the correct orbit.
The second propagator that we are going to use in this course is called the SGP4 algorithm, which stands for the Simplified General Perturbation Algorithm. Now, explaining the details how this algorithm works is beyond the scope of this course. But if you are interested, there are papers explaining how the algorithm works. Now, this algorithm is much more accurate than the Keplerian motion or the two-body motion because it takes many aspects into consideration. For example, it takes the non-uniform gravitational field of Earth. Now, this is not a new algorithm. It was developed in the 1970s, and it was secret, but then it was made public in 1980s, and there were also new improvements even recently in 2020. The nice thing, it is relatively fast and computationally efficient, but it is not faster, of course, than the Keplerian algorithm. So Keplerian algorithm is very simple, and it's much faster to obtain, to calculate than the SGP4. Now, there are more advanced propagation algorithms, which also require more simulation time or more calculation time. Now, given its popularity, you can find codes in both Matlab and Python to generate the SGP4. So all what you need to do is to input, as we saw at the beginning, input the TLE elements, also input the start and the end, so the simulation time, to the SGP4, and then you can get the position of the satellite at different time instances. We will see an example in the next slide, how to use Matlab, built-in function in Matlab, to generate an orbit.
Let's walk through an example in Matlab of how to generate an orbit and propagate that orbit using SGP4 and using the two-body Keplerian method. So first I'm starting by clearing the variables and closing the windows. So I'm just putting the word hidden here because if any previous window opened by the satellite simulator will be closed. Now we need to specify when do you want to start the simulation, when do you want to stop it. So I'm putting in some arbitrary date here. So you can put the year, month, day, and hours, minutes, seconds. The stop time is the start time, and I want to simulate the orbit for 30 minutes. You can of course increase and decrease. Now this is the sampling time, so I'm asking the simulator to simulate every second in these 30 minutes. Now this command will create the scenario, which with the start time, the stop time, and the sampling time, which is 1 second. Now what I'm going to do, I'm going to create two satellites. The first satellite, so I defined an altitude of around 400 kilometers, so I added on top of the Earth radius. I identified the eccentricity to be 0, so that's a circular orbit. Now I defined the inclination, the right ascension of the ascending node, the argument of periapsis, and throw anomaly, etc. So now I'm creating the satellite, and so I fed all these parameters. So you can of course check the documentation. You always can press on the function and press F1, or you can Google it. So you can see the syntax of how to write the command. Now If you scroll here, I didn't specify anything else, so let's try. I'm gonna just start one by one. So now I'm just clearing, I'm creating the scenario, now created the satellite. So let's have a look here. What do we see here? We see the satellite parameters, and then we see the orbital propagator. So by default, Matlab uses SGP4. Now let's play the scenario. So this will take a minute to load. Now when it loads, so here's it loading, and so let's rotate here. Here's the satellite that we just created. So you can change the time playing speed, and you can advance the time and see where the satellite would be. Now note here, the orbit looks like Earth. It looks like fixed, but it's not really the case. Look at the background. So the stars are moving. So our camera is fixed on Earth. So that's why we're seeing the Earth is not rotating. But actually, you can change also the setting, so you can fix the background and makes the Earth rotating. So that's a homework for you to try. Now let's continue. I'm gonna create another satellite, but this time at the end I'm gonna specify that I need a two-body Keplerian propagator. So you see here, orbit propagators, and I'm specifying the two-body Keplerian. So let's run this, and at first I'm gonna close the so that's maybe optional, so let's try to run it without closing. Yep, so you don't need to close it. So let's look at the second satellite when I created it. So it specified the propagator as two-body Keplerian. Now let's go back to the and we're putting both satellites. So the first satellite is using the SGP4, the second is using the Keplerian. Now note there's a slight difference between the two orbits. This is due to the different implementation in Matlab for these two propagators. Now on the long run, now this might be some programming thing in implementing the orbits, but on the long run these orbits will deviate to each other. So if I run this for example 20 or 30 for example rotation or orbits, you'll find that two satellites will have different location. Of course, as we saw in the lecture, the two-body propagator is less accurate than the SGP4 algorithm.
A typical satellite antenna can rotate in the elevation and the azimuth direction. So what we've done in the previous slides, we have shown different methods to calculate the satellite orbit. Now we will see how we will use this satellite orbit to point the antenna towards the satellite. In a low Earth orbit satellite, the satellite is passing for a short period, let's say within 15 minutes, the horizon of the user. So this is a typical satellite dish or satellite antenna, and you can see the mount here. There is an elevation motor. So here's the elevation motor that can rotate the antenna up and down, so it will change the elevation angle. But also, as you can see from this mount can rotate around the azimuth. So here, this mount can rotate around the azimuth. So if you input certain azimuth and elevation to the controller will point the antenna towards the satellite. And remember, in a LEO satellite, you have to keep active tracking for the satellite if you want to communicate with that satellite during a given period. And also we say that GEO satellites, and we will see that in the simulation, that GEO satellites are also moving slightly and thus require also some kind of tracking, especially if you have a very large antenna with very narrow beam width.
I have modified a bit the previous satellite scenario, so now we have a better orbit passing near to Melbourne. So you can play the scenario and you can see the satellite is moving. So what I'm going to do now is I'm going to create a ground station. So this ground station is, I took the coordinates of RMIT University. So if I add this, not here, so we'll now have a ground station here in the CBD. So what I'm going to do now is to track the satellite with respect to this particular ground station. So in particular, I would like to know the azimuth and elevation of that satellite with respect to the ground station. So you can also obtain the range, which is the distance. This is very important later for calculating the free space path loss for communication, for calculating the signal attenuation between the satellite and the ground station. What I'm doing also here, I'm creating a time vector. So basically this is just a time variable. So if I run this with F9, so what you'll find here is that just the time will be nicely presented as the x-axis. So I'm plotting here the elevation across the time. So here's the time, it's 8 minutes, and here's the satellite path. So during the simulation time, the elevation of the satellite started from around 6, went all the way to around 20, and then back to 0. So note that you could have a negative elevation, that's okay, but that means the satellite is not visible, it's below the horizon. Now, we can also plot the satellite path in the polar coordinates. So in the polar coordinate, remember that this point is the zenith, is the point above our head. It's directly above our head, so this 90 degrees, 0 is the horizon. So that circle here is the horizon, and that arc here is the arc where the satellite starts and ends its path.
We have reached the end of this lecture. Thank you for watching. Looking forward to see you in the upcoming lectures.